Light is something you think you understand. It's hitting your eyes this very moment. You've been surrounded by light from the day you were born, so it's familiar, right? But here's the catch. What is light? Can you actually explain it? The answers people usually give are vague. It's energy. It's waves. It's photons. Okay, but what does that really mean? Those are just words, labels. You're naming the mystery, not explaining it. It's like asking what fire is, and someone just says combustion. That doesn't tell you anything at all. It's just a replacement of one word with another. Here's what gets to me. Light is the very thing that lets you see everything else, but you can't actually see light itself. You see objects because light bounces off them, but the light that travels through the air from a lamp to your eye, can you see it? No, you can only see where it comes from, or where it lands. But the light in transit, moving through space, is invisible. Think about that. The very thing you depend on to see the world has never actually been directly observed by you. And nobody seems to find this strange. In classrooms, we teach children about light with pictures of rays bouncing like billiard balls, and everyone nods, assuming that explains it. But it doesn't. The truth is, light is one of the most puzzling phenomena in the universe. Everything you think you know about it is either incomplete or flat out wrong. And this isn't a new issue. For over 300 years, scientists have argued over the true nature of light. Isaac Newton, the legendary physicist, was adamant that light is made up of particles. He called them corpuscles, tiny light bullets that shoot out from sources and travel in straight lines, bouncing off objects and entering your eyes. This seemed logical. After all, light travels in straight lines. It bounces off mirrors. It casts sharp shadows. These are things particles do. But then there was the opposing theory. Christian Huygens, a Dutch scientist, argued that light is a wave. He could explain phenomena Newton couldn't, like why light bends when it passes through water, or why you see colored fringes around shadows. Waves do that, not particles. In 1801, Thomas Young performed his famous double-slit experiment, which seemed to put the debate to rest. When light passed through two slits, it created interference patterns, bright and dark bands on the screen. This behavior is characteristic of waves. Case closed, right? Well, not exactly. A century later, everything fell apart again. Einstein showed that light is made of discrete packets, called photons, when he explained the photoelectric effect. When light hits metal, it knocks out electrons one by one, just like particles. So, which is it, particles or waves? This is where things get messy. The truth is, the question itself is flawed. The answer is neither one nor the other. Light is something entirely different, something that doesn't fit into our everyday understanding of the world. It's not a particle that sometimes acts like a wave, and it's not a wave that sometimes acts like a particle. It's something else, something that forced us to rethink everything we knew about reality. Once scientists accepted that light is a wave, they faced an even bigger problem. Think about every wave you've ever encountered. Water waves move through water. Sound waves move through air. Waves move through a medium. They're disturbances that travel through something. So if light is a wave, the big question is, what's it traveling through? What is light waving in? This question haunted 19th century physics. After all, light travels through the vacuum of space. There's no air, no water, no nothing out there. So how could light possibly be a wave if there's nothing for it to wave in? The answer, they thought, was simple. There must be a substance that fills space, a medium through which light waves could propagate. They called it the luminiferous ether. It was invisible, massless, and transparent, yet it must have been there to carry the waves of light across the emptiness of space. Scientists began hunting for this ether with great enthusiasm. They built elaborate experiments to detect it. One of the most famous of these was the Michelson-Morley experiment in 1887. Their idea was simple. If the ether existed, light should travel at different speeds depending on the direction of the Earth's motion relative to the ether. If the Earth was moving through the ether, light should travel faster when moving in the direction of motion and slower when moving against it. They constructed incredibly sensitive instruments to measure this speed difference, expecting to detect it. But they found nothing. No difference in the speed of light, no ether at all. This should disturb you. Light, it turns out, is a wave that doesn't need a medium to travel through. It propagates through empty space, through the vacuum, without any medium to carry it. This is one of the fundamental aspects of light that doesn't match anything we experience in the everyday world. Every other wave you've ever encountered relies on something else, whether it's water, air, or people. Light doesn't follow those rules, and this is where things start to get even weirder. There's an experiment you might have heard of, a famous one that shattered our understanding of light and reality itself. Picture this. You have a barrier with two thin slits cut into it. You shine light at the barrier. Behind it, you don't just see two bright lines where the light went through the slits. Instead, you see an interference pattern, a series of alternating dark and bright bands. This pattern, created by light, is something that only waves can do. As the light waves pass through both slits, they spread out, overlap, and interfere with each other. Where the peaks meet peaks, you get brightness. Where they meet troughs, you get darkness. This is definitive proof that light behaves like a wave. Case closed, right? But here's where things get truly bizarre. Now here's the twist. What if you turn down the light source so that you're emitting one photon at a time? That's one particle of light per emission. Each photon hits the screen as a single point, just as a particle would. Fire another photon, and it lands at a different point on the screen. It behaves like a particle should. But then, keep firing these photons one at a time, and wait. After thousands of photons have hit the screen, what do you see? The same interference pattern, bright and dark bands. Now think about this. Each photon was sent through the slits one by one. There's no way for them to interfere with each other. And yet somehow each photon seems to know where the bright bands are, and it avoids the dark ones. It's as if each photon is going through both slits simultaneously, interfering with itself, and creating a pattern that makes sense only for waves. But wait, you thought this was a particle, didn't you? This experiment suggests something radically different. What you're seeing here is not a wave or a particle. It's both, and neither. Light behaves in a way that defies classical expectations. A photon, in this case, appears to act like a wave and a particle, depending on how you measure it. The question, is it a wave or a particle, is completely wrong. The nature of light doesn't fit into either category. It's something else entirely, something that exists in a strange realm of quantum physics. So, let's stop pretending we can fit light neatly into boxes. The question itself, is light a wave or a particle, doesn't even make sense. What we call light doesn't operate in the familiar world we experience every day. The world where things have clear positions, defined paths, and move at slow speeds. When we talk about light, we're not dealing with ordinary stuff. We're dealing with something that lives in the strange, counterintuitive world of quantum physics. At the quantum level, concepts like wave and particle don't exist the way we think. These are just labels, approximate descriptions we use because that's all we have. In the quantum realm, light is described by something called a wave function, a mathematical object that encapsulates all possible states of the system. The wave function doesn't tell you where the light is. It tells you the probability of finding it in different locations when you measure it. So, when we say light behaves like a wave, we're describing the probability of where a photon might show up when you measure it. And when we say it behaves like a particle, we're describing where that photon actually lands when we measure it. But in between those measurements, light exists as a quantum object, existing in a superposition of possibilities. This is why trying to categorize light as one or the other, particle or wave, is an oversimplification. The truth is that light, like many quantum phenomena, transcends our everyday concepts. It's not that it's one thing sometimes and something else at other times. It's that it's neither, and it's both, depending on how you interact with it. This duality isn't just an academic concept. It's something that works in real experiments. It's how we get lasers to work, how we build quantum computers, and how we understand atomic structures. It's what makes modern technology possible. But it's also something that completely breaks our conventional understanding of the world. Now, this might all sound abstract, but it's crucial to understanding the very nature of reality itself. You see, light isn't something special or unique. What's special is our perception of it. You might think that light is one of a kind, something different from all other phenomena, but it's not. The truth is that everything we see, all the electromagnetic radiation we encounter, is the same. The only difference is the wavelength, the distance between the peaks of the waves. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they're all part of the same family, just with different wavelengths. Your eyes, however, can only detect a tiny sliver of this spectrum, a narrow band of wavelengths between roughly 380 and 700 nanometers. This tiny slice is what you call light. Everything else, the waves you can't see like radio waves or X-rays, is still electromagnetic radiation. It's just outside your perception. And this perception is not because of some mystical property of light. It's because your eyes evolved to detect the types of electromagnetic radiation most useful for survival. The sun emits most of its energy in the visible spectrum, and objects at Earth-like temperatures reflect light most efficiently in that range. That's why your eyes are tuned to see visible light. But color? Color doesn't exist out there in the world. There's no red in a 700 nanometer wave or blue in a 450 nanometer wave. Color is something your brain creates. It's a label your mind applies to distinguish between different frequencies of electromagnetic radiation. The same goes for brightness. What you see isn't the objective world. It's your brain's interpretation of electromagnetic fields. What you think of as the real world is just your brain's model of light. It's not the territory itself, it's the map. And the map is far stranger than you've ever imagined. This brings us to a deeply strange concept. Light doesn't experience time. I mean that literally. From the perspective of a photon, no time passes. If you could see the universe through the eyes of light, everything would appear frozen. Let me explain why. You know from Einstein's theory of relativity that time slows down as you approach the speed of light. This is not some abstract idea. It's real and measurable. Atomic clocks on airplanes and satellites run slower than those on Earth. This effect gets more extreme the closer you get to light speed. At 99% of light speed, time slows down significantly. At 99.99999%, time almost stops. And at exactly the speed of light, time doesn't exist. For light itself, there is no journey. There's no passage of time. When a photon travels from a star billions of light years away to reach your eye, from your perspective, it took billions of years. But from the photon's perspective, the journey is instantaneous. That's a profound realization. The speed of light is not just a speed limit on travel. It's built into the very fabric of space-time itself. It's the maximum rate at which causality can propagate, the fastest that anything can influence anything else. And this is where light's true power lies. Light carries the electromagnetic force. It's not just what allows us to see. It's what governs interactions at the most fundamental level of reality. Electrons repel each other because they exchange photons. That resistance you feel when you push your hand against a table, that's photons being exchanged between the atoms in your hand and the atoms in the table. Every electromagnetic interaction is mediated by photons. Even the structure of your body, your DNA, the molecules that make you who you are, is held together by photons. Light isn't just a tool for vision. It's one of the four fundamental forces of nature. Everything you experience in your daily life, every force, every interaction with matter, is influenced by light in some way. From the very structure of matter to the movements of electrons inside your cells, light is working invisibly behind the scenes. You might think of light as just the thing that illuminates the world, but it's far more than that. It's the glue that holds everything together. Now you might be thinking, okay, fine, light is strange, but why should I care about all of this? I just flip a switch, and the light comes on. What's the big deal? Well, this is where things get really interesting. Understanding light is about more than just trivia. It's about understanding what reality actually is, the very nature of existence itself. Every single thing you think you know about the physical world is incomplete, even flat out wrong. Take solid objects, for instance. You think they're solid, right? But they're not. They're clouds of electrons repelling each other electromagnetically, held in place by forces mediated by photons. When you touch something, you're not actually making physical contact. Instead, you're feeling the electromagnetic forces pushing back against each other. The so-called solid nature of the world is an illusion created by the invisible dynamic forces at play between particles. Seeing, too, isn't just passive reception. When you open your eyes and look at something, light is striking your retina, triggering cascades of electrons, which cause chemical reactions and send electrical signals to your brain. You're not just receiving information, you're actively participating in the creation of the images you see. It's an electromagnetic interaction, not just the simple act of light entering your eye. Your brain constructs every image you've ever seen from patterns of photon impacts. That's reality, constructed by light. The universe, in essence, isn't made up of physical stuff. It's made up of fields, quantum fields that permeate every bit of space. What we think of as particles are just excitations in those fields. Light is the way we access, interact with, and manipulate these deeper layers of reality. It's how we probe the structure of atoms, communicate across vast distances, and even look inside the human body without ever having to cut it open. MRI machines use electromagnetic fields to create images of your organs, and solar panels convert photons directly into electricity. Every fiber optic cable that transmits data across continents relies on light to carry the signal. Every one of these technologies works because we took light seriously. We didn't just settle for the simplified view. We studied it, understood it, and harnessed it. But even with all this, light still holds mysteries. The fact that we can use it to build technologies that seem miraculous to someone from just a few hundred years ago, that's the power of light. But the real miracle is not that we can use it. The real miracle is that we can understand it, even if that understanding is not at all what we expected. You wanted to know what light is? Well, here's the best answer we have. Light is oscillating electromagnetic fields traveling through space at the maximum speed allowed by the universe. It's not a wave in any medium. It's not a particle in the classical sense. It's something different altogether, a quantum object, an excitation in the electromagnetic field that carries energy, momentum, and information. When we measure it in one way, it looks like a wave. When we measure it in another way, it looks like a particle. But it's neither of those things, not in the traditional sense. It's something that incorporates both, depending on how we measure it. The behavior of light depends on our interaction with it. The light we observe is not the light itself, but our observation of it. And that's why understanding light means understanding the nature of observation, of reality itself. But even this answer is still a simplification. The truth is, the more we understand about light, the more we realize how much we don't understand. The more we uncover, the deeper the mystery seems to grow. And that's the beauty of it. We've unraveled a lot. How light shapes the universe, how it mediates electromagnetic forces, how it reveals the structure of space-time. But we're only scratching the surface. Light may seem familiar, even ordinary, but in reality, it's the most extraordinary thing in the universe. And the deeper we look, the more we see that light isn't just what allows us to see. It's the force that shapes everything around us, the force that keeps the universe together. So why is this important? Because light isn't just a tool. It's a window into the deepest mysteries of existence. It's the very foundation of our understanding of space, time, and the universe itself. Light defines our reality. Without light, the world as we know it would cease to exist. The way we see the world, the way we interact with it, the way we understand it, all of that depends on light. It's not just about making things visible. Light gives us the power to probe the structure of matter, to communicate over vast distances, to understand the deepest laws of nature. When you think about light in this way, it becomes more than just a simple phenomenon. It becomes the key to everything. It's the pulse of the universe, the medium through which we perceive the world, and the force that governs everything we experience. From the tiniest atoms to the largest galaxies, everything depends on light. It's not just something we see with our eyes. It's something we use to understand the universe at its most fundamental level. And the more we learn about light, the more we realize how much there is still to uncover. The story of light is the story of the universe itself. As we wrap up, it's clear that light is more than just what we see or use. It's the very foundation of reality itself. The speed at which light travels, the fundamental limit that defines space and time, plays a crucial role in maintaining the order of the universe. Without this boundary, the fabric of reality would unravel, leaving behind a chaotic, unpredictable cosmos where cause and effect no longer hold. Light isn't just something we passively observe. It's the force that shapes every interaction, from the tiniest particle to the vastest cosmic structures. Through light, we probe the universe, unlock its mysteries, and connect with distant worlds. Understanding light, even just a fraction of it, brings us closer to understanding the very nature of existence. As we continue to push the boundaries of our knowledge, one thing remains clear. Light isn't just a phenomenon we study. It's the key to unlocking the mysteries of the universe, and the more we uncover, the more we realize how much there is still to discover. So the next time you look at a beam of light, remember, you're not just seeing the world. You're witnessing the pulse of the universe itself.